Greetings, friends. Randall Nagy here. Welcome back to the BLT report. And in this built-in report, we are simply going to focus on the single built-in set class. And the set class is probably something you're familiar with if you've taken any training whatsoever. So we're going to go ahead and do a deep dive on the set class by first introducing you to a type report that we felt we would like to share with you now that we've covered the static method. Located in typereport.py, it has a total of 7 operations, from creating a report on what two types have in common, to simply doing a type report on either the public, private, protected, or all member functions. If you never used an enum before, here's a good example on how we can import as well as create our own qualified global members, so as to allow us to take a look at all the different type of reports that we could have, for example, public, private, or all combined. Running the type report for our set class, you'll notice that we have a total of 17 unique functions. A lot of these things are very intuitive if you know anything about Venn operations and common high school level mathematics here in the United States and elsewhere. The most important thing, I think, to be aware of is the things that set, for example, would have in common with dictionary, as well as what set would have in common with our ubiquitous lists. Items 1 through 3, of course, are common throughout, but set bridges the operations between dictionary and lists by either having a update, which we have in dict, or remove that we have in set. Truly a unique as well as overlapping collection class. We all probably know that when we use set as a class going through its initialization routine, that we're going to iterate through any sequence type, as we see here. But whenever we use the curly braces rather than getting a dictionary, set is smart enough to understand when we are using an instance of set rather than an instance of dictionary. Another thing to note about set is that the collections are eccentric. Although Python's dictionary went eccentric in its ordering for a while, it's now sane once again, but set is still a little crazy. So if we were going to sort a set, of course would return our interval properly sorted, but set of course would mess it all up again and put in any order that it arbitrarily felt was a good order for our sorted collection to be in. Another thing to notice about set is that we have been using it a lot in our training. And unlike we saw with strings, we don't see any caching, at least in CPython at the time of this recording. So if I create a set with the elements of CAT, I'm going to get another set. But as we mentioned, the C and the A and the T are certainly going to be cached. But more importantly, and to the point here, we can indeed subtract sets from each other using the minus sign to see that when B is removed from A, of course, we're going to get an empty set. Because the help documentation is just so self-explanatory and very excellent on the built-in collection types, and I believe that because the Python built-in collection types have been with us for so long, is a primary reason why the documentation is so good. For example, very short, we see that add is simply going to add a single element to a set, of course, only if that element is not already in the instance of that set. Clear is easy to understand. It's going to move all the elements from a set. Copy, of course, will return a shallow copy of the set. As we mentioned, shallow copying is a default, and we talked a lot about that previously. Just remember that when we have a shallow copy, we're getting references to what's collected. And while the set may be a new instance, items that are collected by the set will be referenced, of course, deleted when nothing else references what we have included in our collections. Difference is easy enough to understand, and of course, we've been using it all over the place, and we simply activate the set.difference member by using the minus sign. And we're going to find that there are many operations we can do on a set, as you probably are aware of, certainly if you've taken my training, by using a mathematical operator. One thing to note here is that the key difference when we're using mathematical operators is that either we're going to assign something using an equal, or we're simply going to return something if no equal is implied whenever we're comparing two sets. Aside from the Boolean operations, which we'll also be talking about later on, we also have the idea of removing something. And here we're going to remove something using the minus and then assign it to ourselves. So we're going to have an instance on the left-hand side, or L value, before we subtract whatever is on the right side of the R value, which of course can be an anonymous reference or dynamically created set. We'll be talking about the caveats of using augmented assignment when we get to the ampersand operator. Discarding is easy to understand because it's simply going to remove an element from the set if it's already a member. Otherwise, it does absolutely nothing. In other words, a very safe operation. It's not going to throw an exception. Whereas when we're using the intersection operation, we have the ampersand. And when we have the ampersand, of course, it's simply a Venn operation, and it is very associative. In other words, we're going to have the collection of the intersection returned to us. But interestingly, if we're going to be using the ampersand equal or the and equal sign, we're going to be updating the set so that if we have a dynamically created or anonymous set on the left-hand side, at the time of this recording, we can have some strange things happen. For example, if we wanted to intercept the ampersand, advanced Pythoneers will probably remember that we're going to be using dunder and with a self, it's an instance method, and then a parameter. And if we are going to take an instance of z, put it dynamically and anonymously into our space, we're going to execute the operation. We're going to return a result, assign it to the underscore as we've seen, and all is well. However, if we're going to try to assign something by adding the equal sign to the anonymous or dynamic instance of z, we're going to have a problem because Python can't find an L value for the augmented assignment, so we can't execute the dunder and function call. The solution is very easy. All we have to do, of course, is create an instance for our L value and optionally create an instance for our R value. And then Python will be able to find the a.dunder and set up the parameter of b, so we can see that we did indeed get our message type. So whenever you see an equal sign, remember, it could be a problem if we don't have a real instance assigned, and all will be well. Disjoint operations are very, very handy. And once again, we're providing the return type of Boolean, just so we have a better set of documentation here. And the isDisjoint member function will return true if there are no intersections between one or more sets. IsSubset works the same way. We can have a greater than. In other words, is the L value a subset of the R value? Of course, we can also use equal. Once again, returning Boolean. And another Boolean, of course, is superset, where we simply put the greater than sign in between our L value and our R value, and also can use an equal sign as well. Of course, because we are performing a Boolean operation, our greater than or equal assignment will work very much as we expect, even if we're using an anonymous type. So our Boolean operations will work out just fine, as we see here. Now, one of the shared methods of the two important ones shared with list is .pop as well as .remove. And as we master one, we're going to master the other, because while pop will return something that's popped off an arbitrary element, remember, these sets are unordered. The only time we'll get an exception is if the set is empty, and that's the same error we'll get when we're using an undefined key value for a dictionary as well. Remove, of course, would do the exact same thing, but rather than using the hash code as we do with set, it's going to simply remove the item and not return it, raising the same key error when the set is empty. Now, symmetric difference is another one where we're going to have a chance to use mathematical notation. And the fun thing about the symmetric difference, of course, is that we're going to have both a return as well as an update, but rather than being left associated, for example, when we're going to use a set to give us the difference between the L value of Yabu, a value that has everything except the exclamation point, or finding that there are no differences because we're left associative, when we reverse those two around, the real power of symmetric difference, and I do use this a lot, is that we will find the difference no matter which way those arguments are presented, either on the left or on the right. So you can understand why something as powerful as symmetric difference would indeed allow us to have a mathematical notation assigned to it, as well as the update and all the caveats that go with it, as we see in operation number 15. Union is the basics that we're all familiar with from high school mathematics. We were simply going to create a new instance of a set and return it, as you may expect. Once again, a very handy operation, almost as handy as our minus sign and frequently used. We simply use a pipe symbol to create a new instance, and to prove that we're going to have a union created, of course, we'll set A to be an empty set, then operate our union on more than one set, which is the case with most set operations, so as to see that the ID of A is still new, but B is a new instance that we've returned, and that after the operation, A is still an empty set, and B, of course, has the return results, as we probably expect. Number last is the update operation. Once again, we have a or equal, which will update our set, so now that A would not be the empty set, and another instance of B would not be created. Our review questions include KA 1032, a legacy question that's also in the book, but we should be confident in asking ourselves, what is the difference between the set of cat and cat when it's created without using the set class? 1, no difference. 2, the number of elements will differ. 3, both perform Venn operations. 4, the instance will be the same. 5, their content will be the same. That's nice. No, none of the above. KA 1033, set differences, another legacy question. What is the Venn difference between set cat and set rat? 1, nothing. 2, the number of elements will differ. 3, either R or C. 4, either CR or RC. Or 5, their differences will be the same. KA 10068, set basics. What will we see when we subtract the set of rat from the set of cat? 1, the set of AT. 2, the set of T. 3, the set of C. 4, the set of CT. Or 5, 2 of the above. 1069, set basics. What will happen with the same subtraction? If we create the sets directly, will we get a 1 AT, 2 R, 3 C, 4 CT, or 2 of the above? Question KA 2034, set comprehension. Also covered in the book. What would our set comprehension contain? If we were going to filter on the condition of A equal to G, would it equal an empty set? 2, G and G in a set? 3, G in a set? 4, a list with a set? Or 5, G and G in a list? That was easy. KA3054 Advanced Set. A new question for today will be covered up in our next book. Set cat with the caret of set rat will give us 1C, 2T, 3CT, 4A, or 5A and T each in the set. Finally, another new question would be how to intercept the ampersand operator. Would we be using a single underamper, a double underamper, 3, a double underamp, 4, a single dunderamp, or 5, a dunderamperand? Say that 3 times. Well, thanks for watching. Very succinct, very short. And of course, we only have 32 more cards to go before we can change that title from 100 Python questions to 200 and more. So thanks for watching. I'm looking forward to seeing you in the bookstore.